Today we'll start with Ohm's law. Ohm's law you all must have done in class 10, and Ohm's law statement is at constant temperature, potential difference between 2 points of a given conductor is directly proportional to current flowing through it. Mathematically we write V proportional to I or V equals to Ri, where this R is the resistance. Okay. Now here what we'll do, we'll try to derive this Ohm's law from the concept of relaxation time and other terms. So let's do the derivation of Ohm's law. In the derivation of Ohm's law, we take a conductor of length L, area of cross section A, under a potential difference V. I is the current which is flowing through this conductor, and capital E is the electric field set up there due to the potential difference which we have applied. And let's assume that a small n represents number of free charge carriers per unit volume. M, this is your number of free charge carriers per unit volume. And a small m is the mass and E is the charge on each charge carrier. So charge carrier here, if you are taking conductor, it will be the electrons. So we'll be taking that m is its mass and E is electric charge on the charge carrier, that is the charge on the electron there. The force on each charge carrier, this will be equals to E into E. This is the force on each charge carrier. So acceleration of each charge carrier, this will be E by m. So if we assume that the drift velocity is Vd, in that case its velocity, that is the drift velocity Vd, this will be your E by m into tau. This tau is mean relaxation time. What is this mean relaxation time? When we have applied potential difference across a conductor, then the free charge carriers of it, they will be now set up into a particular direction's movement. That means during their movement, they will be colliding with other electrons, they will be colliding with the ionic core, but still due to the potential difference applied, that is the electric field setup, they will always try to move in a specific direction, that is the direction set up by the electric field. So the distance, like suppose you have one free electron here, it is moving, it is colliding with other free electron or the ionic core, then it is changing its direction. Now here it suffers another collision, again it will change its direction, suppose it goes like this. So that way it will suffer different collisions and it will be moving there in a specific direction. The distance moved between two successive collisions is called free path, whereas the time duration between two successive collisions is called relaxation time. So if you consider the average value of these relaxation time, that means it will be the mean value of relaxation time, that is the mean value of the time duration between two successive collisions. Like if I take suppose tau 1 is the time here for first collision, tau 2 is second, tau 3 is third. If you take the average value of all such relaxation times, then we get mean relaxation time. So this tau is the mean relaxation time. So we can write again this electric field in terms of the potential difference, because you know that as electric field is negative of potential gradient. If I have set up an electric field E for a conductor whose length is L kept under a potential difference V, so basically you will find that electric field can also be written as the potential difference, which is V here across the conductor of length L. So it is your V divided by L. dr will give you the length here, so it is your L. So electric field we can also write V by L. So if you substitute this, then what we will get? Vd will be equals to EV by L by M into tau. In place of E, we have substituted V by L. So this is now suppose our equation 1. Drift velocity, this is E by M, V by L into tau. Also, as I is NEAVD, this is the expression for electric current in terms of the drift velocity. So from this, if you take expression for drift velocity, this will be your I by NEA. Let's call this as equation number 2. Now we have the equation 1, which is your Vd equals to E by M, V by L into tau, and this is your second expression. So from equation 1 and 2, if you take, then it will be given as E by M, V by L into tau, I by NEA. Or V is equals to M by NE square tau L by A into I. If you transpose the terms there, you will get this expression that V is equals to M by NE square tau L by A into I. Now, if you look at the term here inside the bracket, then this particular term M by NE square tau L by A, this is a constant for a given conductor of a particular material at a particular temperature. This particular term is a constant for a given conductor of a particular material at a particular temperature. Because for a given conductor, this term like M NE square will be a constant. For a given conductor, L and A will be constant, and at a particular temperature, this tau will be constant. So if this term is constant, then obviously what we get? V proportional to I, and this is your Ohm's law. So this is your Ohm's law, and in the statement of the Ohm's law also we have said that potential difference between 2 points of a given conductor of a particular material at constant temperature is directly proportional to the current flowing through it. So this is your Ohm's law. We can use this expression as V is proportional to I as V equals to Ri. Let's call this as equation number 4, where R is the proportionality constant, which we call it as the resistance. So now, if you compare equation 3 and 4, then we can get the expression for R. in place of R, this entire term is coming. So we can write R equals to from equation 3 and 4, R is equals to M by N square tau L by E. This is the expression. Now, again, you can see this M by N square tau is a constant for a given material at a particular temperature. So, if M by N square tau is constant, then what we can say that R will be proportional to L. This implies that R is proportional to L and inversely proportional to A when M by N square tau is constant. And when it is constant, it is a constant for a given material at a particular temperature. So this what we get from this one. This is the dependence of resistance. Dependence of resistance on physical factors. That is, resistance of a conductor is directly proportional to its length and is inversely proportional to area of cross section. So this is the relation which we get. Also, if you just combine these two, so R will be proportional to L by A, or we can write R is equals to rho or L by A, where rho is a specific resistance or a resistivity. This is the expression. Rho is a specific resistance or resistivity. This is a constant for a given material at a particular temperature. Okay. Now, using this one, before we get the expression for a specific resistance, if you just use this one and you want to define a specific resistance, in that case, what we can say, as we have R is equals to rho L by A. If L is 1 unit, A is 1 unit, then R will be equals to rho. So this we can use to define a specific resistance. So this is the resistance offered by the conductor or material of unit length and unit area of cross section. This we can also define in a different way, as it is the resistance offered by cube of that material whose side is unity when current enters from one face and leaves from opposite face. Suppose we take a particular cube whose side is unity, and this is made of that particular material. This is 1 unit. Each is 1 unit. So if the current enters from one face, so what will be the area of cross section? This will be 1 unit. If it leaves from the opposite face, then the distance through which it has passed, that is also unity. So we can say that resistance offered by this cube made of that material will be numerically equals to a specific resistance if this cube has unit side and current is entering from one face and leaving from other one. So this is how we define a specific resistance. If you take the unit of a specific resistance, rho will be R A by L from this expression. So this is your resistance, area of cross section by length. So the unit of rho, a specific resistance, will be ohm meter, because it is ohm meter square by meter. Ultimately it will be ohm meter. So this is the unit of the specific resistance. Now let's take what expression we get for a specific resistance using these two equations, equation 5 and equation 6. This is the expression for a specific resistance. Okay. There is one more term that is called as the conductivity. Conductivity will be the reciprocal of resistivity. So conductivity, if you take, this is 1 by resistivity. So that means conductivity, if I represent by sigma, this is 1 by rho, and this will be your n squared tau by n. This we can use to get the expression for conductivity. This is the expression for resistivity. So resistivity of the material will depend upon mass of the charge carrier, charge of the charge carrier, and also on its number per unit volume, apart from the term mean relaxation time. Now you see, we know that if we increase the temperature of a conductor, then its resistance increases. Why it will happen like this? Because if you are increasing temperature, then the charge carriers, now they will possess more amount of energy, they will have more thermal energy, so they will move more rapidly. As they move more rapidly, they will have more frequent collisions, and if they have more frequent collisions, then duration between two successive collisions will decrease. So you can see, if this rho is decreasing, then obviously a specific resistance will increase. And if a specific resistance increases, then resistance of the material will also increase. This is why when we increase temperature, resistance of conductor increases. For semiconductors, there is different thing. For semiconductor, if you increase the temperature, then resistance decreases. There it is decreasing because with increase in temperature their bonds, covalent bonds which are there, they break. There will be more number of free charge carriers available for conduction. So there will be more free electrons, and per unit volume there will be more holes present there. So as they will be more, so that means this n will increase there. And if n is increasing for semiconductor, a specific resistance will decrease. That is why resistance of semiconductor will decrease with rise in temperature. So this was the derivation of Ohm's law, and we have done up to different stages there. We have derived up to Ohm's law. The same derivations you can use if it is asked to show that how the resistance of a conductor is directly proportional to length or inversely to area of cross section. So you can do up to the stage where we have done the dependence of resistance on physical factors. Sometimes you may be asked to derive the expression for a specific resistance or conductivity. So you derive up to this stage or this, whatever have been asked in the question. So this was the discussion on derivation of the Ohm's law from the concept of relaxation time.